all. Welcome to Penn's Power Corner. I'm your host, Ali Ashoka, the interim editor-in-chief of Power Electronics News. Today, we'll be speaking with Vijay Mangtani, Vice President of the Power IC Business Unit at Allegro Microsystems. Vijay, very glad to have you here.
Very nice to meet you, Alia, and thanks for giving us opportunity on this platform.
Oh, no problem. So we're here to speak about Allegro's patented Power-Through portfolio. This was a technology that originated from the 2022 Heyday acquisition, right? And maybe you can talk a little bit more about the core innovations behind Power-Through and the benefits behind the technology.
Certainly. So, if you look at our industry today, our customers are driving to reduce power loss, increase efficiency. They want smaller systems that are lightweight so that they can keep up with the market demands in AI, power, as well as um, electrical vehicles. And everybody's in the race to innovate their end products. So time to market is really, really important. What it means is they want solutions that are easy to implement in terms of design and easy to implement in terms of EMI. So what does Power-Through bring about in this case? Power-Through essentially simplifies the traditional way of designing gate drivers, which is done with a power supply, an isolated gate driver channel, which requires engineers to do a lot of work to design the circuit, lay out the circuit, and use multiple components on the board. What Power-Through does is brings innovation that uses a single channel to deliver power as well as control signals. The result is much superior gate driver capability in much smaller footprint and reducing the power losses, improving efficiency, at the same time improving EMI. So that allows customers to get to market faster as well.
Okay, great. And how does Power-Through differ from traditional isolated gate drive architectures?
That's a great question. So in terms of traditional gate drivers, um, many switches are not ground referred. So customers need to generate isolated floating power supplies. This is usually done with an isolated DC-DC converter. The standard norm is to use a flyback converter. Flyback converters require large transformers and generate higher EMI. And then you need a gate-driven isolation channel. So typically, a design will have a lot of external components. It will use a lot of PCBs. And since we are dealing with high voltages in these applications, the spacing between external components need to be carefully planned, laid out so that not only it works functionally, but it's at safe distance from each other and still doesn't generate a lot of EMI. That's a really challenging task. What Power-Through does is uses a proprietary modulation scheme to use a transformer in a full bridge configuration. So transformer no longer needs to store and release energy like a flyback does.
Mm.
And we are able to run this transformer at much higher frequency than flybacks are typically run in similar applications. So the core is really small. And now, as I mentioned, transformer is sending power and control through the same isolation barrier. So instead of the two isolation barriers of the traditional system, we have single isolation barrier, modulation and power delivery are self-contained, size is smaller, and by doing this, by carefully designing this transformer, we are able to reduce common mode capacitance. That gives us a significant advantage in reducing EMI and the power dissipation in the systems.
Yeah, actually, I saw that. That was going to be my follow-up question. I've seen figures showing up to a 15x reduction in common mode
Yes.
capacitance compared to alternatives, and that reducing EMI by up to 20 dB. Are there other design aspects that Power-Through addresses?
Certainly, but before we go to other aspects, I would
Yeah,
like to expand on your question on
yeah.
the EMI also. So, um, as customers try to improve efficiency, they are moving from standard architectures to multi-level converters. So, in a given power factor correction system in AI power, historically, A standard architecture was used. New architecture now uses many more switches. And it's not uncommon to see 18 to 24 switches in a three-phase power converter that's doing the power factor correction function. So now, you know, let's take a 15x reduction of the capacitor and multiply it, multiply the advantage across 18 to 24 times. Additionally, the second factor that's happening is that newer wide bandgap power devices switch much faster. That's what enables higher efficiency in addition to the new circuit topologies of multi-level converter. When these devices switch faster, the DVDT is very high. So common mode capacitance produces a lot of current from the high voltage side back to the controller side. By reducing this capacitance, we are able to reduce currents injected, especially when you are using multiple gate drivers in the system, these add up, that allow us to use much smaller footprint because now we are reducing the filter components required for EMI.
Mm.
As the other advantages are inherent reliability of the system. By reducing the bill of material components, we are reducing essentially failure points. And the secondary aspect of this, but not um, you know uh, something that really is valuable, is the common mode currents when they get injected in the ground, they potentially can cause ground bounce, and that can make the controllers make wrong decisions.
Mm.
So all these innovations add up to simplicity of design and faster time to design with fewer engineering efforts.
Okay. I'm kind of curious, how has the technology been adapted from controlling GAN FETs to SiC FETs? Because I know there was the earlier the GAN FET controlling GAN FETs; those products were released earlier, and especially given that silicon carbide typically requires higher gate drive voltages and has
Yes,
different switching frequencies. So, just how
yes.
was the technology adapted?
Oh, that's a great question. Yes. So silicon carbide, as you mentioned, typically requires much higher voltages. Allegro has a lot of base technologies, including our proprietary SG8 BCD technology. This BCD technology allows us to efficiently integrate power switches up to 100 volts. Typically, silicon carbide gate drivers require 20 volts or lower. So using our proprietary technology, we're able to scale up the design after acquisition. We are able to offer output voltages up to 20 volts positive and minus 5 volts negative. Some of the silicon carbide gate drivers require strong negative gate drive to provide noise immunity and the efficiency performance. And we have made our gate drivers scalable. So customers can choose output voltage they need for a particular silicon carbide device to get the best possible efficiency and operating point. Additionally, they can use the same gate driver from silicon carbide switches from multiple vendors, which requires different voltage levels. So this reduces the supply chain complexities, and a common design platform can be used in a much more flexible way.
The silicon carbide gate driver portfolio, it includes both the HV 85311, so that is an integrated solution with the internal transformer, and then there's solutions that require external transformers. What are some of the design considerations that engineers should evaluate when choosing between these approaches, and are there trade-offs that exist between these solutions?
Definitely. So we provide these two distinct paths to our customers who are, uh, you know, um, looking for different solutions. They have their preferences. So when you look at the integrated solution, it is very much plug and play. So it just fits and reduces design time. But in certain cases, customers want a lot more flexibility on how to lay out their PCBs. Um, Sometimes they prefer to put components in a certain way to achieve their objective. And sometimes they prefer to have more granular control of their supply chain. So by offering the both solutions, we are allowing them to meet their specific need for a specific project.
Okay, okay. Um, Actually, this is alluding to what you were stating earlier. That there's elimination component counts. Uh,
Yes,
there was 25 components for data center PFC, and 70 plus in
correct.
automotive OBCs. Can you
Yes.
walk through some of the, specifically which components Power-Through eliminates, and does and you already mentioned this. It goes beyond tangible savings towards in reliability and thermal benefits and power density as well. But maybe
Yes.
we could just walk through some of the specific components.
Definitely. So, as we discussed earlier, the traditional gate driver designs are essentially implemented with a bag of parts. So, now the challenge is that power supply is designed independently of the gate driver. So, a lot of components are required to tune one with the other. These are typical passive components, resistors, capacitors, and such. Sometimes customers really need to put some additional active components also, and they add up uh, when you, again, as we discussed, sometimes the layouts need to meet certain spacing guidelines. When you combine this, uh, it's not uncommon to see 13 to 18 components elimination per channel. So that's really significant.
Yeah. Yeah. Um, so maybe we could talk about just more about the applications. So I know Power-Through is addressing applications spanning data centers, power supply, right? EV OBCs and industrial motor drives, right? Are there applications that are showing a faster adoption rate, and are there specific technical or business drivers that are accelerating this?
Certainly. So we are seeing a very strong pull for both AI power and electrical vehicles, and both are really pushing the limits of adoption. So when we look at them specifically, in data centers, the deployment rate and the increasing power density with the newer um, uh, AI processors is ever increasing. So the volumes are really climbing fast there. Now, as you look at the constraint of availability of the power, the focus on efficiency forces customers to use multi-level converters versus traditional converters, use newer wide bandgap devices versus the traditional devices. That's where the adoption rate increases. And XEV is a similar story. Um, you know, Better mileage through battery charge is enabled by smaller weight, better efficiency. So the technical dynamics are very much parallel in both applications. The content is increasing, and there's demand for higher performance solutions.
Okay. Um, Thank you so much. Well, I mean, I have I read that the patent portfolio is growing quickly. How so, and what areas do you see this growth?
Certainly. So, as we look at newer architectures, um, they require certain additional features. As we look at ever increasing power densities, there's a lot more focus on even making power through smaller and smaller and smaller.
Mm.
So the patent portfolio is focused on improving the efficiency, reducing the size further, and adding additional intelligence that make the system smarter.
Okay, okay. Um, Thank you so much, Vijay. I have no further questions. Was there anything else you might have wanted to add?
Yes, definitely. So when we look at Allegro's portfolio, uh, uh, when we specifically talk about these applications, one thing we should certainly keep in mind is our current sensors. We have our new generation of current sensors with TMR technology,
Mhm.
which improve the detection speed and provide sensing bandwidth of up to 10 megahertz. These are best-in-class devices that work very well in these systems along with our isolated power supplies and provide a complete solution to the customer. So not only they can drive the device efficiently, but they can protect them as well as get the current feedback for the control loop using our TMR current sensors.
Okay. Um, is it all right if I ask a little bit more about the TMR sensors? I was, could you kind of elaborate on maybe the benefits of TMR sensors versus traditional current sensors, shunt-based current sensing?
Certainly. So when you use a traditional shunt-based current sensor, it's the current is converted into voltage across the shunt.
Mm.
So there are losses generated because of that, whereas TMR is magnetically coupled. Current is sensed without um, electrical contact from the power side. So that allows us to provide a lossless solution. And by not connecting the TMR to the power carrying conductor, inherent isolation can be provided. The customers can implement the solutions easily. They don't have to deal with the isolation barrier
Mm.
that they have to deal with a current sensing shunt and remove the power losses.
Very exciting stuff. I won't take up any more of your time, Vijay. I really appreciate it. Thank you. Thank you for connecting, and I'm excited to see more IP development around the Power-Through portfolio as well as the TMR sensing technology.
Thank you very much. Thanks again for giving us this opportunity on this platform. Really appreciate it.